Hello everybody. Welcome to the second progress report for my atmospheric sensor with remote display capstone project for EET 2960 through the Talwar College of Engineering and Computer Sciences at Indiana Tech. My name is Kyle McNeese, and today I will be covering a summary of this presentation, the final proposed system design, the list of components, final budget, standards and constraints, a prototype, the second revision, testing results, a video demonstration, a timetable, and conclusions. The summary of this presentation, I will go over the proposed design and how it solves the need to measure conditions of an isolated environment, which is at the heart of why I chose to do this project in the first place. I will also go over the components, budget, and purpose of each using a table that also explains the purpose of each component. I will be showing a before and after for the prototype versus revision 2. I will show testing results and reasoning for the improvements I made for this progress report. And lastly, I will show a video demonstration of revision 2 functioning. Now, the final proposed system design for that, the sensor node contains, of course, the ESP32 microcontroller and the BME280 sensor. This system is very simplistic, and there is not much to it, and it is meant to interface with the display node. Now, the display node contains, of course, another ESP32 microcontroller, an LCD screen, an LCD backpack module, and 3 buttons. Figure 1.1 below shows the block diagram for the whole system, and this is a very general block diagram. Now that I've made extra improvements, if I were to fully write out the block diagram, there would be some extra buttons from the ESP32 going back to this ESP32 from the sensor node, indicating that it is controlling this. I prefer this just to show the very basic idea of what's going on. My list of components here shows the 2 ESP32s that I've been using for both nodes, breadboards for both nodes, the BME280 sensor module for the sensor node, the 16:2 LCD screen for the display node along with the backpack module, 3 push buttons here for a reset, mode select, and measurement request for the display node, and then USB-C power cord and outlet bricks for each board, as well as various jumper wires I've used for both circuits. The final budget here shows each component, as well as quantity here, total cost, and whether or not I needed to purchase these things. Recently, I had to add these push button switches here because I didn't actually have enough to do some of the functions I wanted to add to the display node, and they're very, very cheap, around 11 cents a piece on DigiKey, so that is included here. Standards and constraints I've had to use 4 standards. This particular set of devices uses the IEEE 802.11 BGN standard for Wi-Fi communication, and for the circuits themselves, I'm exclusively using I2C communication, and this part here is important, the 3.3 volt logic. Whenever you're working with modules in an electronics project, and microcontrollers as well, you have to be aware of the logic levels used. Some are 5 volt logic, some are 3.3 volt logic, and if you don't know and just try to work with what you got, either if it is a 5 volt logic and you're using a 3.3 volt logic microcontroller, such as the ESP32, it may not work fully as intended, or if it's the opposite and you're using a 5 volt logic board such as the Arduino boards with a 3.3 volt logic chip or module, you will actually destroy that module by giving too much voltage to it. So very important to keep this in mind. Now the sensor node constraints uses 5 volt USB-C power, and it needs to be able to be controlled by the display node. I'll talk a little bit more about this later. This was recently discovered as a necessity for the design of the system. And the sensor node is going to be accurate within plus or minus 1 degree Celsius, plus or minus 3% relative humidity, and plus or minus 1 millibar. The display node uses 5-volt USB-C power because both of these use the same microcontroller which powers the circuits. Now the display node also needs to be able to reset the sensor node remotely. And this is important. Again, I'll talk about this more later. And it also needs to be able to manage data retrieval. Now, the first working prototype I had is here. Here on the left, figure 1.2 shows the sensor node prototype. And this prototype I originally assembled on the breadboard given to us by Indiana Tech as part of the electronics kit. And for those of you that are aware of how big that board is, it was completely unnecessary to keep the sensor node on a board of that size. It's just an unnecessary and inefficient footprint for what I was doing with this circuit. Figure 1.3 shows the display node prototype, and this works fine, but there were some improvements to be made and some functionalities to be added. Here on this slide, it shows figure 1.4. This is the sensor node on the new, smaller breadboard to make more efficient use of the space and the footprint. And figure 1.5 shows the new display node. I have since moved the LCD screen and backpack module down to the left to make room for these 3 push buttons here, as well as I've gotten rid of the wires for the voltage and ground here, as well as these wires which would be connecting to the microcontroller. So here you can see the yellow and orange wires here, as well as the red and black wires there. The orange and yellow are for the data communication between the LCD screen backpack and the microcontroller, and then the red and black are for voltage and ground respectively. I got rid of those so that these buttons here are more accessible. As well as I slightly changed the format of the LCD screen, the temperature and humidity. Now, the testing results and obstacles. The tests clarified the need to remotely reset the sensor node. So I ran multiple overnight tests to see if the next morning I could retrieve data, and sometimes it worked, sometimes it didn't. And all that meant was I would need to go into the room where the sensor node was and physically reset the ESP32 board, and then I would be getting good data again. Now this is a drawback for sure for the system because the purpose of this system is to be able to remotely measure ambient conditions in an isolated environment, i.e. I should not be going into the room to mess with this device to get it to work. As well as the 24/7 web server that I had mentioned in previous presentations, it's not really required. It doesn't need to stay online 24/7. It only needs to be up and running when being measured. So that brought the need for a measurement button on the display node. So here I actually took a video demonstration of using those 3 buttons on the display node and how they work. So here it turns on and shows the IP address that it's connected to on the local network, shows the new format. Now that first button takes the measurement from the sensor node. The second button changes the page on the LCD screen. And the third button resets the sensor node. And that is what was very, very important in making the isolated environment truly isolated so I don't have to go in there to reset the board. Now, as you can see here, we have our timetable. This red line here indicates where we are at. We are at the end of week 10 here. So I have already made my improvements on the second prototype. I have another week to make any improvements I may think of before focusing with this last week on the reports and presentations for the final for this class. So the improvements, just to reiterate, I've added sensor node controls to the display node. I've improved the wire routing on the display node and gave a basic user interface to the display node. Now for the future, for I or somebody else possibly improving this design, a 3D printed enclosure could be created. We could reduce the footprints further by designing a PCB for each node, and we could incorporate an option for a Bluetooth keyboard, which goes hand in hand with changing the architecture to allow for non-local network communication. So an idea I had was I keep the sensor node at home connected to Wi-Fi, but if I'm out and about and have the display node with me along with a Bluetooth keyboard, I could type in the network that I'm currently on and have it communicate back to the sensor node. This is a more complex coding architecture, so I chose not to do that for this capstone project just because of the amount of time and obstacles that it would add, but that is something I would love to add in the future for this design. And if you have any questions, feel free to get a hold of me, email me. I'd love to talk about it. And thank you for your time.